Now, there are many different types of NEMA designs in three-phase motors. We'll look at B first. There's a chart here to show the typical performance of the various designs. And look at curve B. It's the one that has the lowest slope up at the operating area. But you notice that it also has relatively low starting torque. Now, it has high starting current, and most of the time current and torque are proportional to one another, but that's when it's operating, that's when it's running. In starting, all bets are off because things are operating a little different. So a NEMA B design has relatively high starting current, and that can be a problem. It has high inrush current. But it has decent starting torque, pretty good speed regulation. What is speed regulation? Well, up in the region where the motor is supposed to operate, near the 100% speed or near synchronous speed, the motor, as torque is increased, the motor speed drops off. The less it drops off as the torque is increased, the better the speed regulation. In other words, the more able the motor is to maintain speed despite torque increases. NEMA B has typically very high breakdown torque, and so that's another advantage because you can really, I don't want to say overload the motor, but you can load it with torque where it has a high torque capacity and doesn't break down and just stop, which is a good thing. So these are used in several different applications. There's a lot of crossover applications between types B, C, and D, but you can see the examples here where these are commonly used. NEMA C, on the other hand, has a higher starting torque than B. It has similar speed regulation, typically not as good, so an increase in torque reduces the speed more in a NEMA C. But it has lower starting current, which is a good thing, right? We don't want to have to size our controls and our wires and things to accept this huge inrush of current into the motor. So lower starting current is a good thing for everything involved. So you can see examples where these are commonly used as well. A NEMA D has the worst speed regulation, but it's similar to B. The speed regulation of these motors is not terrible. They're usually relatively flat. But a Type D has a higher starting torque than Type C even, so it's the highest starting torque of what we've got. And lower starting current, so at least relative to B. So those are all good things. The problems with it is that it's not as good at speed regulation as Type B, for example. There's a bigger difference there. So relatively it's poor speed regulation. And it's called, therefore, a high slip motor. What does that mean? Well, that means that it's operating farther away from its synchronous speed at full load. And so, as a result, it has a lower full load speed. But these are still used, and all of the applications take advantage of this type of motor. Now, one thing about speed regulation is it can actually be an advantage to have relatively poor speed regulation. If all of a sudden a very large torque is required, the speed is not going to change very rapidly, and that's a good thing. Think of an elevator. Do you want the elevator to accelerate all of a sudden and jerk you? No, of course not. So a Type B design would be a horrible choice for a motor in an elevator, whereas a Type D would be a much better choice because it would reduce jerk. Now, you can kind of get the best of both worlds by using a slip ring motor. And basically what this does is it has connections to the rotor itself. Remember, the rotor are these bars that are conducting current that are induced in them. Well, if you have electrical connection to those bars and you can increase and decrease the resistance in those bars, well, then you can change the behavior of the motor and really simulate the Type B, C, and D design. So you can have one motor that, depending on the particular operation, can change its behavior. So you can get the advantages of all the motors: the low jerk at the beginning, the relatively high torque, whatever you want. You can tailor the motor's operation on the fly, essentially. Now, what about wiring? Well, there's so-called 4-pole, 4-wire non-grounding. Let's look at that first. So you see that it's a star configuration where the ground, the system ground, is labeled W. So that's our reference potential. And we've got the 3 phases, X, Y, and Z, as plugs. And you can see how various types of plugs are wired to the various phases. And then there's 4-pole 5-wire. Now what does a pole mean? Well, a pole is something that conducts electricity. You expect it to conduct current. Okay. So a 4-pole, the poles are the 3 hot legs and the W, the system ground. Those are the lines that you expect to conduct some current. Whereas the ground, you don't really expect to conduct current. It's really there for an equipment ground to prevent people from being shocked, right? It's there in case things go wrong. And so you can see 120 volt, 208 volt, 3-phase plugs there on the left, and 277, 480 volt 3-phase plugs on the right there. Then there's 3-pole 4-wire grounding. So 3 poles, we expect only 3 of the wires to conduct power, right? And those are X, Y, and Z. And then the ground, in normal operation, should not conduct power. This is a 600 volt plug. And then you can see the on the other side, the 3-pole 4-wire grounding. So again, the 3 hot legs conduct power, but the ground should not. So it's 3-phase 480 volt. And of course you can get motors for all of these. There's a wide variety of motor voltage. Some motors are made to operate on multiple voltages. And so you've got different, obviously different characteristics of the motor in terms of the torque they can provide and so forth. But some motors operate at multiple voltages. It just depends on how you wire it. Now you don't typically have a motor where you operate it on different voltages. If you're thinking you might reduce the voltage in order to reduce the motor's speed, that's not really a thing. That doesn't really work. Now you can reduce the voltage going to a motor in order to reduce current to make more of a soft start. But at operation you can't adjust the operating speed by changing the voltage going to an AC motor. That doesn't work. Now you can change the speed of an AC motor, but we'll talk about that a little bit later. You have to do something different besides changing the voltage. A motor starter is something that's always required, and you might wonder why this is. Well, notice we're talking about voltages that are a lot higher than usual. You've probably been shocked at one point in your life by 120 volt AC. You lived through it. Not pleasant experience. I've been shocked by 220, for example, more than once, so I guess I didn't learn my lesson the first time. That hurt. I prefer not to be shocked by 220. As a matter of fact, I've got a funny story I'll share with you. A friend of mine, when I was working at Amatrol, was one of the field service technicians, and I guess in his early days he had studied some electronics and knew about multimeters and small circuits and things, and then he thought, well, I'm not sure I want to do this, and he decided maybe he wanted to be an electrician instead. And when you study electronics, usually that's more of a college type thing or technical trades school, but the trades are really dominant for electricians and things. So there you get more on the job training. Yeah, you might learn something in the classroom, but a lot of what you learn is on the job. So this guy wasn't sure which way he wanted to go with his career, and so he was helping an electrician. He decided to work under him and learn from him, and so I guess you call that a journeyman. And so he was working with this guy, and he noticed the guy didn't carry a multimeter. Now this is an old electrician, been doing it 30 years, and the guy didn't carry a multimeter. And so my friend realized there are different electric voltages or electric potentials in a home or a business. And he said, so he asked this old electrician, he said, so how do you tell the difference between 110 and 220? And the guy said, well, you lick your fingers and you put them on the 2 wires, and if it tingles right here, then you know it's 110. If it hurts real bad, then that's 220. At that point, my friend decided, I think I'm going to go back to the electronics world. He decided he didn't like that test, I guess, very much. So how would you like to have a switch where every time you go to turn the motor on, number one, you have to flip the switch, right? A lot of times with big industrial processes, you need computers and PLCs and things to do the controlling. But let's just say that you want to flip the switch every time. How would you like it when you have to have a big knife blade switch like from Frankenstein to switch 600 volts, and if you touch it, you're dead, right? That's no good. So because of the higher voltages, because of the fact that automated controls are so necessary, motor starters are also very necessary, and they're basically like a big light switch. That's basically the way you can think of them. Now there's more to it than that, because often you have the switch itself, which is called the contactor, and it's not just one single contact. It's 3 switches that happen all at once to connect all 3 phases. You don't want to leave just one phase live. That's a bad idea. You need to turn them all off. But then often there's also an overload protector that mounts onto the side of the contactor that senses the current going into the motor. and can help to detect when the current is not is too high, or maybe there's mismatch. A lot of times what happens in the industrial world is that one of the legs, the hot legs, will go out, so you'll lose a phase from the power company. Until they get it fixed, you have to live with it. Well, what do? Well, the problem is that three-phase motors can burn themselves up pretty quickly because they don't have enough power to rotate, so sometimes they'll just rotate slowly, or they will just lock up. And what happens is all the power going into them then is simply heating them up. It's not actually being converted into much rotational power. And in that case, if you lose a phase, it's very important that motors be shut down, three-phase motors at least. And so a lot of times these overload protectors, or generally motor starter protectors, I shouldn't say it that way, it's not a motor starter, it's a motor protector, includes the ability to sense not just overcurrent, but losing a leg where there's no current in one of the legs and current in the other two, and will automatically just cut the current to all of the motors. Now, another feature in these can be, well, you see manual and magnetic, both operate switches. And what does that mean? Well, a lot of times in these motor starters there's an override. You can manually go and flip a small switch essentially to force the motor to turn, or you can just press it and it'll make it turn. That's the manual portion. Sometimes there are manual switches where you have to operate it by hand. Those are not all that common, but it doesn't matter which type it is, both throw switches. It's a very common feature to have a reversing motor starter or a reversing contactor. It turns out in three-phase motors, if you want to make the motor turn the opposite direction, all you have to do is reverse any of the two power leads. It doesn't matter which two. Just interchange two of them, and the motor will turn in the opposite direction. So that's a very common feature in these contactors, is the ability to just switch out two of the legs by switches, and it'll turn in the opposite direction. There are also commonly reduced voltage starters, and again, the purpose is not to control the motor speed at the operating speed. The purpose of a reduced voltage starter is to reduce the jerk at the beginning of the motor's motion. And then there are also dual speed motor starters. Now you have to be careful with this. A dual speed motor starter is not something where you can take a single speed motor, get a dual speed starter, and all of a sudden you've got a two-speed motor. It doesn't work that way. Two-speed motors have multiple windings so that they can accommodate two different speeds. So in overload protection, what commonly happens is the coils overheating is sensed because of excess current. So you've got excess current going through the protection, the overload protection, and it basically just cuts out the control circuit so that the motor shuts off. So if you know anything about electronics, you can understand the schematic down here. You see the motor off on the right with the thermal switch mounted in the motor, and that would go to the controls. I don't think it's shown here, but it would also commonly be in line here or going somewhere else. Let's see, high temperature on overload heater due to excessive current opens control. Yeah, so this is not using the motor temperature switch directly. Sometimes that motor temperature switch cuts out power to the motor itself, so it prevents the motor from turning. And what will happen is it's just a bimetallic thing, and so when the motor cools down, it connects again, and the motor can turn on. So sometimes it's not. You don't want the motor to have thermal protection where it controls the motor directly. You want it to be external wires you connect to your control system, because if the motor overheats, you want to fix that problem before the motor comes back on. But sometimes, again, these are just built into the motor and interrupt the wires to the motor itself. It depends on the motor. But anyway, you can see the circuit here, how there's a transformer that steps down two of the legs to provide some control power. You can see the fuse there, you can see the stop button. But how does this work? Well, when the start button is pressed, then the circuit is complete, and you can see that the relay coil M turns on. Well, it's not shown here very clearly, but that coil is what pulls in the three switches that are labeled M in line to the motor, right before you see the OL, the three OLs. So that's how you turn on the motor. You push a button, and basically the motor starter is like a relay. And so it's a magnetic thing where you pull in the switches, and usually there's another switch that then bypasses the start switch. You can see it here labeled MA, and that continues to provide power to the coil, so the coil doesn't just turn on and off. If you understand that, great. If you don't worry. You'll understand it once you go through controls. The point is that once you press the start button, even when you release the button, the motor continues to run with the starter. And also there's these overload switches, and the way they work, the overload that you see, those sort of half circles together there, they don't actually disconnect the circuit there. All they do is they change a switch state. So by default, these allow a switch to be closed, but when there's too much current in any of the three legs, it opens up a switch, which is the same as pressing the stop button. That cuts out power to the motor coil, not the motor's coils itself, but the relay and the starter. And then that opens up the three switches labeled M that are in line. Okay. Now, sometimes these overload sensors are called heaters in the starter because they're basically like a circuit breaker, except that they don't break right there. In a circuit breaker, it's a bimetallic switch that literally breaks, but in this case, it's sort of a heater that triggers a switch. And then there are, fuses as well are a common way of protecting a motor, but a lot of times too you sense, for circuit faults, if there's a ground fault where a hot leg is connected to ground, so too much current is flowing through ground, and you see that labeled MCP, the motor branch circuit and short circuit protection. So generally what we've got here is, again, a disconnect device, branch circuit protection, motor control devices, which the motor starter is part of, and motor protection devices. So you see those two boxes. Really, the motor starter and motor protection device are often built into one unit, or they're connected together. And you can think of the overloads as operating three switches to cut it out. Now, there's so-called 2-wire and 3-wire starters, and what's the difference between those? Well, on the right you see what's called a 2-wire control. And the reason it's called 2-wire is because the control, the start-stop button, there's just 2 wires going to it. That's all you need. And all it does is make or break contact so that the motor turns on or off. Now, often this is not a switch. You might think of this as a toggle switch, like your light switch, where once you move it into position it stays there. But most often the way industrial controls work is they are momentary switches, because a lot of times the command to start something is, right now I want you to start the motor. So you push a button, motor starts, you release it. Well, that was then, right? 10 minutes later, if you're caught in the machine and it's sucking you in, you don't want the motor to continue going, right? You don't want to have to reach that toggle switch and turn it off. You want to be able to hit an E-stop, an emergency stop that hopefully is close by so that you're not killed in the thing, right? So toggle switches are not all that common in industry. Momentary push buttons are more common because it gives you more flexibility and more ability to shut the machine down without it just automatically restarting. This is an exception to that, because usually this is not a toggle on-off switch. This is usually something like an automatic control system where when the tank level gets too high you need to pump liquid out, and so there might be a float switch at the top, and that's what actually does the on-off control of the motor. Now, you got to be careful with these. These are not all that common, but they do exist, so you need to be aware of them. This is an automatic type of control, and it's not a bad thing. It's just it has to be implemented in a case where it's safe for the motor to simply come on automatically without anyone being there or deciding it. So you've got to be able to trust the machine, I guess, for it to turn itself on. So that's 2-wire control, and often that start-stop thing is just a sensor somewhere. But there's also what's called 3-wire control, and the reason it's called 3-wire is because you need connection to either side of the start button, but you also need connection to the stop side. So the controls that go to the control cabinet or the control box, whatever it may be, requires 3 wires. And this is a little more complicated control. This is where you more often will see the start and stop buttons on industrial machinery. That's 3-wire control, because you have to have 3 wires to wire up the controls. But both, their function is to start and stop the motor. Now there's a NEMA size number for the motor starters themselves for 3-phase power, so that's another little table that you'll need later on. Now, we talked a little bit about brake motors early on, and a brake motor is commonly used as a failsafe. So if there's a loss of power, the brake is energized by a spring frequently, and that makes the motor stop turning. But there are other ways to stop a motor. You can actually reverse two of the legs, say in a three-phase motor, and try to get the motor to operate in the opposite direction. And so what will happen then is that you just apply power until the motor stops, and the motor will come to rest very rapidly. Now, you have to be careful with this. If you have an application where you need to start and stop the motor many times, remember, using a plug stop will actually damage the motor fairly quickly. The reason is because all of the energy that the motor has, its rotational energy, say you just disconnect the power, all that energy, plus then when you reconnect the power backwards so that you're slowing down the motor, all of that power has to be absorbed by the motor, so the motor heats up. And remember, heat is the main thing that damages motors. So this is kind of, if you're doing this over and over, you're really heating the motor over and over, and it can overheat and then fail. So plug stop is something you have to be careful with, but it is an option, and it's sometimes a very good option. You can also use resistors, though. So a resistor is where basically you let the motor turn a little bit longer, but it acts as a generator, so it's generating power, and that power runs through a resistor. You can actually stop a motor fairly quickly with resistors. This works fairly well. And then rather than the motor converting all that power into heat, the resistors do it. And you're saving your motor in that case. And resistors are made for dissipating that heat. Sometimes you even would put a fan on these resistors so that they don't overheat as well. Now, a forward reverse starter is shown on the left, and basically if you look at this carefully, you'll notice that the forward windings connect the legs in one direction. The reverse windings reverse just two of the lines. It's L1 and L2 that are interchanged, and you should know by now that that would cause the motor to turn in reverse. One of the big things is that you don't want both the forward and reverse contacts on at the same time, and often it's not possible with a good forward-reverse contactor. But your controls need to be set up where it doesn't look like you could turn both on at the same time. As I said, a two-speed or a dual-speed motor has multiple windings, and so you might use a very similar setup but different purpose motor starter to connect the legs to the motor, where you either connect to one set of windings or to a different set of windings. And so that way the motor goes either fast or slow. A reduced voltage starter is a variation on this, where all of the contacts go essentially to the same windings on the motor, but now there's some resistors in line with two. So you might start the motor with contactors A, the auxiliary contactors, and that way there's resistance in line, so not as much current goes to the motor, and so the motor starts softer. Now understand, you wouldn't run it continuously this way because you wouldn't generate full power. You'd generate full speed but not full power in the motor. Well, assuming you can reach full speed. But then a lot of times what happens is you just switch in then the main contactors so that the motor can have full power at the rated speed. Now, the motor controls themselves need to be protected, and so there are motor control enclosures. Now understand, this is not the motor, this is the controller. So this is where you'd put your contactors and things like that. Often you don't put the motor control in, or you don't put switches and things in the motor controller enclosure. Sometimes you do, most of the times you don't. This is where the contactor goes, and the contactor needs to be protected because really that's what turns the motor on, and you don't want the contactor to accidentally turn the motor on because a mouse is in there pressing it or something. So there's various different possible problems and things that need to be guarded against, and that's what the motor control enclosure does. As you can see, these NEMA design numbers, and I would leave it to you to read some of these descriptions of what these control enclosures protect against. But this is not the motor, this is not the contactor, this is the enclosure for the contactor, essentially. Now, a synchronous motor is also an induction motor, but it's a little different. It operates at no slip. So it operates at exactly the synchronous speed. Now, if there's enough torque that forces the motor to slow down, a lot of times the motor will just come to a stop. So synchronous motors are good because they're guaranteed to operate at a particular speed as long as you don't overload them. Now, they do typically have very low starting torque. So to get them started, you usually start with a separate induction coil on the motor. So you operate the motor as if it's just an induction motor to get it to start, and then you turn on the synchronous windings to get it to come up to synchronous speed. Now, what do we mean let's consider some speed portions. When there's no load, an AC motor should operate at its synchronous speed or very close to it. How do you calculate the synchronous speed? Well, you take 120 times the frequency over the number of poles in the motor, and that will give you the so-called synchronous speed. Now, in an induction motor, the speed decreases as the torque increases. You saw that in speed regulation in the torque speed curves. So the motor's not designed to operate at no load. It's designed to operate at its full load. Its full load rated speed is not the synchronous speed. It's a little less. And so a lot of times if you do the calculations, you find that synchronous speed is, say, 1800 RPM, but motors are rated often to run at 1720 RPM. That difference of 80 RPM is due to slip in the motor. Of course, a synchronous motor would operate at 1800 RPM, and because they would operate with no slip. What is a motor pole? Well, you don't really have to understand it, but it has to do with the number of windings. So if you notice here, there are 3 separate windings because we're going to have 3 phases. But you'll notice that one of the winding pair, well, I should say there is a winding pair. And the way this works is there are wires coming out towards you. Remember from, probably you saw this in physics where a vector is represented as an arrow, so there's a point on the head of it and feathers on the tail. So you usually indicate the backside of the vector with an X. That's what's happening here. So current would be flowing out at us, say out of the red coil on the right side, the arrow pointing toward us, and you can't see it, but there are windings or wires that connect then to the other side, you see, to that feathered side, the arrow, the back side of the arrow. But then that current continues and comes through the other arrowhead and then back in through the feather, so that the current is sent through 2 separate windings. Now, is that 2 poles? I think so. I can't remember. It doesn't matter. Always on the nameplate there is an indication of how many poles the motor has, and that doesn't really matter because on a decent motor with a good nameplate, they'll tell you what the rated speed is anyway. But here's a table of taking this equation and then calculating what the synchronous speed would be and then what the typical full load speed of the motor would be. So 4 poles, 1800 RPM is a synchronous speed, 1725 is a reasonable and very common. I think I said 1720 a minute ago. It'll vary a little bit because this is just the 95% of synchronous speed that they're listing here as the full load speed. But anyway, so you don't have to go through this equation all the time, but you can if you know the number of poles in the motor to calculate the speed. Now, a lot of times you don't want the motor to operate at just one speed. You want to be able to vary the speed of the motor, and so there are electronic devices to do that. And basically what these things do is they take in the current, the AC current, they rectify it and change it into DC, and then they generate a new AC signal from it. So they generate new AC power. They basically synthesize that power. Pulse width modulation is a really common way to do it. A lot of times the motor is used sort of as a, how can I explain this? It's used as a smoothing out device. A low pass filter would be the way to describe it. And you'll see more about that here in a second. But basically it takes the power and changes it from one frequency to another. And that's what we really care about. So that you have control over the frequency, because the speed of the motor is dependent upon the frequency of the current coming into it, not the voltage, at least in AC motors. And so these electronics are often called inverters or drives, or VFD stands for variable frequency drive, VSD is variable speed drive. It's all very similar. There are a few different techniques for doing this, but they usually look something like this. They have relatively high power electronics inside of them for switching the current, because they have to be able to switch the full current to the motor, which is a decent amount. And the actual voltage put to the motor a lot of times looks like what you see in the figure on the upper left side, where basically you're just turning the current on and off to the motor. And so the motor basically takes that and smooths it out as far as the voltage goes, and ends up as a low-pass filter just seeing essentially a sine wave that's at whatever frequency you want it to be to control the motor speed. So you can see how that works. A lot of times these drives can be operated manually, where you have a knob on the front, or you change the motor speed via buttons. A lot of times also they have connections where you can connect them to a PLC and control them automatically and change the drive on the fly, or change the speed on the fly through the drive. There are other ways to do this besides pulse width modulation. I'm not as familiar with some of the other methods, but there are also silicon controlled rectifiers, that's what SCR stands for, that can do essentially the same thing. Now, I don't want to focus on this part so much as the motor. Some motors don't, I don't want to say don't like, they don't respond well to switching voltage across their coils. And so a motor has to be so-called inverter rated to use these. Now, does it have to be? Well, no, not really. A lot of motors can take this abuse, this switching of voltage on and off very rapidly to their coils. And so you won't overheat many motors even when they're not inverter rated. But if you want to be guaranteed that the motor will work with a variable speed drive and therefore be a variable speed motor, then you can use a motor that's inverter rated. Now there are some clever ways to overcome this. If the problem is that you need multiple capacities, there's a way to overcome this. It was actually a clever idea I saw when I was looking at a case study on the Galt House. The Galt House is a hotel in Louisville, Kentucky that actually consists of multiple buildings, and they actually heat and cool their space by geothermal. So they have access to an aquifer that's 600 feet in the ground. And they basically use the thermal mass of water to add and remove thermal energy, and they save, I think it's something like $20,000 a month. And this was back when this case study was written, probably in 2000 or so. So they're probably saving even more today on this system. And basically they need the ability to pump water from the aquifer up. Okay, so you can imagine they've got some pretty decent pumps. If I remember right, they've got two 100 horsepower pumps and they've got one 75 horsepower pump. And the 100 horsepower pumps operate in an on-off manner. You can turn them on or you can turn them off. But the 75 horsepower pump has the ability to modulate the flow, right? So I'm sure they've got a variable speed drive on it, and they can, and I'm sure it's all automatic, but the control system can request more or less flow from this variable speed pump. Well, what do you do when you're up at, let's say you start off with the 100 horsepower pumps off and you start off with the 75 horsepower pump, and maybe you just need a low flow, so you provide, say, 30 horsepower or so, and whatever flow that is, that's what you need. Okay. Well, as you need more and more flow, you ramp up the power to that pump. And so let's say you peg it out, you're at 75 horsepower, but you need more. What do? Well, you turn on a 100 horsepower pump, shut off the 75 horsepower. And then that 75 horsepower allows you, since it's variable, it would allow you then, if 100 is not enough, well, turn back on the 75 horsepower pump and ramp it up, right? And when you get to 175 horsepower, you need more power, no problem. Turn on the 100 horsepower pump and shut off the 75 horsepower pump, see? So it's a nice way of not requiring, 300 horsepower inverter, which would be a heck of an inverter. So it's a clever way to reduce the cost, because while these inverters have come down in price, they're still relatively expensive. A lot of times they'll cost more than the motor itself that's being controlled. So, and of course, the bigger they are, the more expensive they are as well.